So hello everyone. So today we'll be doing a problem. The problem is design of secondary beam of a raft. Okay. So it is design of secondary beam of a raft. Secondary beam of a raft. Okay. So now the problem that is given to us is that the raft is a 3 by 5 pattern. Okay, 3 by 5 pattern given to us. So what does it mean? There are actually 3 rows and 5 columns. So let us see the configuration, how will it look like. So 3 rows and 5 columns, if I just like this. So 3 rows, 1, 2, and 3 rows. Okay, and 5 columns, 1, 2, 3, 4, and 5 columns. Okay, so column spacing is given 5 meter center to center. Okay, so I'll show it here. Both ways. Both ways the spacing is 5 meter center to center. So this one is 5 and this one is also 5 meter. Now the next thing is given is the corner columns are 500 kilonewton load. Corner columns are 500. Exterior columns, how many other exterior columns are there? There are 8 exterior columns. And it is having 600 load. So 1, 2, 3, 4, 5, 6, 7, 8. So 4 into 500, 8 into 600. And remaining interior columns are how many? 3. So it's the remaining 3 are having 8 into 800 loads. So 3 into 800. So the total load, if I calculate, it will be total load 4 into 500 plus 8 into 600 plus 3 into 800. So all total, if I calculate how much it will become, just check it. 4 into 500 plus 8 into 600 plus 3 into 800. It is 9,200 kilonewton. So that is the load that is being falling. And then what is the next thing that is being told here? That 2 secondary beams are introduced in each span of the raft parallel to the short direction. So the raft will be like this. Suppose if I consider the raft panels, if I just consider the panels here. So Sorry, I'll just erase it. So 3 rows. So 1, 2, 1. So you can see here, if there are 3 rows, 1, 2, and 3, and 5 columns, 1, 2, 3, 4, 5 columns. So the panel we get like this. The panels we get like this. Okay. So what is being said? The two beams are introduced in each span of the raft parallel to the short direction. So this is the short direction. This is the short direction, and two beams are introduced in each span of the raft. So suppose in one panel like this, each span. It means this is one span. Okay, this is one span. In one span, there are two secondary beams are introduced. Secondary beams are those beams whose ends are also beams. That is called as the secondary beam. Those beams whose endpoints are also beams. Okay, so now these are introduced in each span of the raft. That means in each span, like this, two secondary beams are introduced in each span in this manner, parallel to the shorter direction. Shorter direction is this, so parallel to the shorter direction this side. Now, SBC of the soil, 50 kilonewton per meter square is given, and materials are given M20 and Fe 500. So we have to design these secondary beams. Okay, so now we have the total load. Total load is given to us. It is 9200. Okay, now what will be the total area of the raft? Okay, so if I consider if I have to consider the total area of the raft, if I take a projection of the like beyond the columns of around 0.5 meter. Okay, so let me show it here itself. I'm showing the projection here itself. So we know that these are the columns. These were the columns 3, 4, 5, 2, 3, 4, 5, 1, 2, 3. And the center to center we know was 5 meter. So if I take a projection beyond the corners of the columns of like 0.5 meter everywhere, it was 0.5 meter and 0.5 meter, 0.5 meter. Okay, it means like this. If I take a projection in this way, it's like a front setback, rear setback, side setback of a plot. Okay, so this is 0.5. Everywhere we are taking 0.5. 0.5 projection. So then what will be the total length here? This will be 5 into 4, 20, 20 plus, it will be 21. And this will be 11. Now area will be 21 into 11, which is equal to 231 meter square. Now, what will be the net pressure? is equal to load 9200 by 231. So it will become, let's check, 9200 by 231, 39.83 kilonewton per meter square. Okay, which is actually less than the SBC of the soil. So SBC was given as 50. So that means it is okay. The area is adequate. Okay. So the net pressure is less than the bearing capacity of soil. Now let us go to the design. So now if I go into the diagram, if I just magnify it a little bit. So I consider these two beams, secondary beams. Okay. So span of the beam will be how much? Span of the beam will be same as this one, 5 meter. Okay, span of the beam is 5 meter. So now in the beam, the load is going, the load goes in the beam from the slab, from the slab. And what area of the slab contributes to the beam? I am repeating, the load on the beam goes from the slab. That means the load from the slab goes to the beam. And what area of the slab contributes to the load on the beam? What area of the slab contributes to the load on the beam? This one. Okay, half of this. Suppose I'm considering this beam. Okay, this beam. So, and half of this slab. This area contributes to the load on this beam. So how will you know the load on this beam? If I try to just so since in every panel it will be same, I'm just removing this panel. Okay, I'm just keeping this part because everywhere the design will be same only. So this part was it, since the secondary beam has divided the panel into 3 parts, so this part becomes 5 by 3, isn't it? Every part becomes 5 by 3. So if I want the length of this part, it is also half of 5 by 3 plus half of 5 by 3. So ultimately this length is this length, this tributary area that I am considering, where this is the secondary beam. So this length also becomes 5 by 3. This length becomes 5. So area becomes 5 into 5 by 3, area of this slab. Okay. Now we already got this pressure, upward pressure per upward pressure value. The upward pressure value was 39.83, right? So now this upward pressure, obviously for design purposes, we have to factor it. So if I have to factor it, if I calculate it, how much value will get factored? pressure is equal to 1.5 into 39.83. Now, going back to this beam. In this beam, the total load that is falling on the beam will be how much? I'll draw it here itself so that you can understand it in a much better way. The total load on this beam will be from the slab, so it will be the pressure into the area. So it will be 1.5 into 39.83, which is the pressure, into area. Area is 5 into 5 by 3. That is the load, total load that is falling on the beam. Okay, now if this is the total load, okay, which is this one is the pressure and this one is the area, 5 into 5 by 3. This one is 5 into 5 by 3, area of a rectangle, pressure into area, total load. And now if I want to convert it into UDL, I divide it with the span of the beam. Span is 5. So ultimately this will be the UDL on the beam. So UDL will become, I consider it as W. Just calculate it. Tell me 5 into 0.83 into 1.5 into 39.83. It's 99.57 per meter. This 5 is the length of the beam, isn't it? And this is the total area, total load. Total load is what? This pressure, 1.5 into 39.83 into area, 5 into 5 by 3. So pressure into area, load by this length is the UDL. So the beam, I draw it here. So this beam will have an UDL on the beam is 99 point, let's check it once again, 99.57. Okay, so kilonewton per meter. Now, this beam is considered as a continuous beam. Okay, this secondary beam is considered as a continuous beam. If we look into the main diagram, okay, this main diagram, this secondary beam is actually like a continuous beam. It will span everywhere. Okay. So this secondary beam is also here as working as a continuous beam. Okay, so when we are designing it, it means design means what? Finding out the AST, and for AST, what we need? We need the moments. And also shear force for the stirrups. Okay. Shear force and moments are required for the area of steel and ASB. ASB is the shear reinforcement. Okay. Now, since the beams are considered as continuous beams, okay, now there are certain coefficients that we use for continuous beams. Okay, where like the coefficients are like for, you see, this is given in IS 456-200 table 12. Okay, these coefficients are for support moment. There are various coefficients are given, which is one is for the support moment and another is for the span moment. So support moment, there are certain coefficients, like for end support it is 1 by 12, next to end support it is 1 by 10, then interior supports the moment coefficient is 1 by 12. Then for span moments, the like interior span, the span moment is 1 by 16, middle of end span is 1 by 12. Okay, so there, whenever there are continuous beams, there are always support moments and span moments, and there are certain coefficients. These coefficients are added to this WL square. Okay, so support moment, if I need support moment at the ends, then it will be WL square by 12, this coefficient. If I need the support moment at ends, which is next to n, then it becomes WL square by 10. Now you see, let's not go into those type of complications. We see that here, as we know that we are always design it for the most criticalities. Okay, we'll just design it for the most critical or severe conditions. So out of these support moments and span moments, okay, in the continuous structure, the highest situation of moment will happen when the coefficient is this one, the 1 by 10, because 1 by 10 is the highest one. WL square by 10 will give the highest value compared to the WL square by 12, WL square by 16, right? Because in WL square by 12 and WL square by 16, the denominator is higher. So what we do is, then the moment will become less, but maximum moment will get when the denominator becomes less. So it will become only when it is 1 by 10. So WL square by 10 will be becoming the highest one. So we don't go into those complications about the end span, next to end span, interior span, different coefficients, and also like span moments, middle of end span, interior spans, these coefficients. We don't go into every part. Okay, one by one. We just take the highest severest condition. So severest condition will happen when the coefficient is 1 by 10. So we consider that. Okay, so maximum, the moment that we will consider is WL square by 10. Okay, so W is 99.57 into 5 square by 10, which becomes, let me just check it, 99.57 into 5 square by 10, 248.92 kilonewton meter. And what is the shear force? Now you see, when there is a simply supported beam, okay, with an UDL, the shear force is very simple. It's like this. Okay, this one is equal this one, and this one is also equal to this one. Okay, and it's like equally divided half. Okay, if this total load is WL, this one becomes WL by 2, or we can say 0.5 L. This one becomes WL by 2. That means half shear force is divided at every point. But when there is a continuous beam, like there are continuity in this beam like this, okay, when there is a continuity, then the shear force does not get actually divided equally. Okay, so when there is, in our case, our secondary beam was continuous. I have shown you in the diagram. The secondary beam was, you can see in the diagram, it is continuous. So suppose this secondary beam, this one is continuous. So in continuous beams, the shear force is not divided directly half-half. So generally what is taken is like at one end the shear force will be 0.4 into WL. At another end it will be 0.6 WL. Okay, so out of this, like the maximum, obviously we take the maximum value. Okay, it is like it is distributed in continuous beams in the term of like 40%, 60%. Okay, because of the continuity. So the out of this 0.6 will be the higher one. So we take the 0.6 WL as the shear force value. So similarly, SF will be 0.6 into 99.57 into 5. So it will become how much? 0.6 into 99.57 into 5, 298.71 kilo Newton. So now we have got the maximum shear force and we have got the moment. Okay, this will obviously the max moment because we have taken the coefficient to be 1/10. If it would have been 1/12, 1/16, then the value will be less. Okay, that's why we took 1/10, which will give us the highest one. Okay, so now from the moment, let us do the design. So assuming width of the beam, we have not taken the beam width, right? So assume this is 400 mm. Now for M20 and FE 500, the moment equation will become mu is equal to 0.133 FCK B D squared. So from here, if I put the exact values of the moment was 248.92. 248.92. 248.92 into 10 to the power 6 is equal to 0.133 into 20 into 400 into D squared. So from here we ultimately get the value of D. So if you calculate it, just check how much you get. Okay, so I'll just do the calculation to 48.92 into 10 to the power 6 divided by 0.133 into 20 into 400. We get around 483.68. Okay, so we let us, since we get around 483 something, 3. So let us consider an effective depth of a little bit higher. So if I consider the effective depth D a little bit higher as 550 mm. So overall depth we take as 600 mm. Okay. Now what will be the AST value? We have every data we have got. So 0.5 into FCK by FY, it is 20 by 500 into 1 minus root over 1 minus 4.6 into what was the moment value? 248.92. 248.92 into 10 to the power 6 by FCK BD square. 220 into B is 400 into D square is 550 square into BD. So 400 into 550. So after doing the calculation, see how much AST you will get. So AST, find out. So it will be 0.5 into CK by FY into 1 minus root over 1 minus 4.6 into, I'll just go back and I'll do the calculation, into 248.92. 248.92 into 10 to the power 6 divided by 20 into 400 into 550 square into 400 into 550. So it is around 1200. Okay, so around 1200 AST you will get. So let us, if we're getting around 1200 something, okay, 1200 something you'll get mm square. So let us take like 25 dia bars. Dia bars. Let us use 3 numbers. How much you'll get? So 3 into area will be pi into area of 1 bar, 25 square by 4. So just calculate how much you'll get. 3 into 3, pi into 25 square by 4. So 1472. I'm giving around 1472 mm square provided. Okay, 1472 mm square AST is provided. Okay, so this is about the moment. Now for the shear, what is the applied shear stress? Tau V is equal to, we have already calculated the shear force before. So what was the shear force value? 298.71. So 298.71 kilonewton, so it becomes 1000 Newton by BD. It is 400 by 550. What is the value? 298.71 into 1000, 400 into 550, 1.35. kilonewton per meter square. Newton per mm square, sorry. Newton per mm square. So now, when we took AST as 1472, then what is the percentage of steel? Percentage of steel will be 1472. It's roughly 0.6%. Just check with the area. 1472 by the area. roughly 0.6% we take. Okay, 1472 by area into 100 by area of the cross section into 100, you get around 0.6% area of steel. So when we take 0.6% and M20 grade and 0.6%, then corresponding to this, we get the shear capacity as tau C as 0.5 Newton per mm square. Now here tau V is becoming greater than tau C because tau V is 1.35 and tau C is 0.5. So we need shear reinforcement for that. Okay. So if I use 10 mm two-legged stirrups, okay, suppose consider 10 mm two-legged stirrups. ASV comes roughly around 157 mm square area of the shear. Okay, if I consider 10 mm two-legged stirrups, the area of the shear reinforcement becomes roughly 157 mm square. So the spacing S 0.87 FY ASV D by VUS. VUS means the applied minus capacity. Okay, so I'll just do it when you'll know. 0.87 FY is 500, ASV is 157 for 10 mm two-legged stirrups. D we have taken 550. VUS means the applied one. Applied shear force was how much? Just check. It was you see 298.71. To 98.71 minus capacity. Capacity is 0.5 into 400 into 550. That means area into capacity was 0.5 tau C into area. Okay, that becomes the shear force capacity, right? Shear force, shear stress capacity is 0.5 into area becomes shear force capacity. Okay, and this 298.71 is the applied shear force. So applied shear force minus the capacity, applied shear force minus the capacity. Okay, so ultimately the spacing you will get it as 185 mm spacing of the stirrups. Okay, so from here we have got this area of steel 1472. Okay, and we have got the three numbers 25 mm dia as the area of recommended area, recommended area for the moment. And here, let me just finish this for the stirrups. Let's finish this equation. Just keeping the units same. Okay, so you will get it as 185 mm. Okay, I'm just keeping the units same. So what was the final output of the secondary beam? So the final output was main steel, three numbers, 25 mm, and size is 400 by 600. 600 is gross, and stirrups is 10 mm, two-legged, and spacing is 180. So this is the final design of the secondary beam of a raft that is given to us. Okay. Thank you for your patient listening.